In this video, we're going to learn how to predict which direction a chemical reaction goes in if it's at equilibrium. So for instance, up to now, we really haven't had to worry about which way the direction goes, because if we don't have anything on one side, then we know that that's the side that has to form products. So imagine we've got an equilibrium, A in equilibrium with B, and we've got an equilibrium constant of 1.45 at 25 degrees C. And let's say we start out with the original concentration of A and B to be exactly the same, 1 moles per liter. And the question is, which way will it go? Will it go to make more B, or will it go to turn B into make more A? So we don't really know. Okay, now if one of these was 0, if we had no A, we know the B must break down to make A. And if we had no B, we know the A must break down to make B. But when we've got A and B, then the question is which one reacts. So in the change on an ice chart, which one would be negative X, which one would be positive X? So the way we're going to do that is we're going to calculate something we call the reaction quotient. And the reaction quotient is given the symbol Q, and essentially Q is exactly the same as the equilibrium constant. We just use the actual concentrations. So although we can use the equilibrium concentrations, we just get the equilibrium constant. We use the actual ones, and that gives us something called the reaction quotient. So very generically, if we imagine we had a chemical equation, AA plus BB in equilibrium with CC and DD, that's the most boring equation there is under the sun, right? The reaction quotient would be the concentration of C raised to that stoichiometric coefficient times by D to the D over A to the A, B to the B, and that is the actual concentrations. So those aren't the equilibrium. If we use the equilibrium ones, right, we get the equilibrium constant. Instead, we use the actual ones. So for this equation at the top of the page, we can form the reaction quotient. Q is just going to be the concentration of B over the concentration of A. In our problem here, right, we've got essentially 1 mole per liter over 1 mole per liter. So again, that just gives us 1. So the thing is, we can use this value of Q to figure out which way the equilibrium will shift. So the question is, how do we know? Well, Q is essentially products over reactants. So if we go ahead and we graph what happens to Q as we run a reaction, let's say over here we have all reactants, and over here we've got all products. So if we calculate a curve for Q when we've got all reactants, essentially we've got numbers down here and our products are 0. So our value of Q would be 0. And conversely, when we've got all products, we've got only a value up here, so this would be big, and our value of reactants would be 0. So I guess that would be infinitely large. But hopefully you can see that the curve will kind of move like so. So at this point here, we've got a value of Q of 0. And as we go to all reactants, essentially this is just going up to infinity. Now, if we compare this to the equilibrium constant, we know that the equilibrium constant is a constant for a given temperature. And so we can basically just draw a straight line. I don't know why I dotted it, but I think it looks cool. And so how do we know when a reaction is at equilibrium? When a reaction is at equilibrium, the value of Q is equal to the value of K. So when we put in the actual concentrations, if they're at equilibrium, then they're the equilibrium concentrations, but that's just the equilibrium constant expression. So we're really looking for this case here. So we know that reactions will proceed along to equilibrium. So if we are down here in the bottom region, in this region here, we've got Q is less than K. So the reaction is going to proceed in order to get Q large and large until it reaches the equilibrium constant. However, if we're at the other end of the curve, if we're right here where Q is much bigger than K, then we know to reach equilibrium, Q must get smaller and smaller until it eventually approaches the equilibrium. And of course, at the equilibrium point, right, so this is equilibrium, we know the value of Q is exactly equal to K. So essentially Q just has to get smaller if it's too big, or it has to get bigger if it's too small, and at equilibrium the important thing is Q and K are identical. So in our last problem we calculated Q to be 1, and we were told K was 1.45. So what that means is that Q is smaller than K. So in this curve here, right, we would be let me see, right down here. And so in order for Q to be equal to 1.45, we have to move to the right. So we have to make more products, and then eventually we'll hit equilibrium and just kind of hang out there. So in this case here, we can say that the reaction of A in equilibrium with B will shift to the right-hand side. So we will convert A into B to reach equilibrium.